Hello, everybody. Hope everybody's good to go for today. I'm going to share the link here. Link to today's live stream. Okay. Link. All right. So things are always changing in this world. I have just discovered that we can, that Google Classroom just updated with access to Google Meet. So I think I will be sending you well, I've already sent it out actually, a Google Meet connection. So that's a link to a meeting that will be an ongoing meeting, and I will make sure that meeting is enabled, and I'll hold some office hours in that meeting at different times, which I'll let you know about. It does look like we are here for the long haul, so we'll see how that goes. We are pretty much wrapping up Equilibrium at this point. Although the ideas will definitely not be lost. We are going to be doing a lot of different equilibrium things moving forward, as the last two units are all equilibrium based as well. So if you have any questions or comments or concerns, just please throw them in the chat. I am writing up the final assessment for equilibrium. I'm not sure. I probably will send that out today or maybe tomorrow. And right now it's a little bit on the long side, so I have to go and edit it down a little bit. The other thing that's going to be happening is we will be moving to the next unit. If there are any of you out there who are needing paper copies of things, I will need to know about that ASAP. I will probably put up a little question on Classroom to see if there's anybody who wants me to produce paper copies. I do have to go into the school to do that, so... Oh boy, I just dried out my throat. So yeah. So I do have to go into school to set up those paper copies, so please let me know. I'm currently obviously not in the school, and but I'm more than willing to go in for you. But I'd just like to go in all together. Do everybody. Not sure what happened there. Okay. I think that got it. Okay. Well, please let me know in the comments. The Google Hangouts is open right now. If you want to drop a comment in there, the Classroom, the live chat is open as well. So feel free to talk to me there. I did try to get a video call going, but that did not fly. So we'll try this for today, and then let me know if you want to. So today we're going to do some more practice questions for equilibrium. I sent you a PDF this morning or last night with a whole bunch of problems on there. And I'm really happy to see a whole bunch of you are online. I've got quite a few viewers here, so that's great. Relatively speaking, at least. We are finalizing up our messages or our marks for the first term here, or the term 3. So I will have those marks settled by. I'm supposed to have them settled in by Wednesday. We'll see. Working really hard on that, and so you might start to see some messages come up finally. I'm sort of finally into the marking groove again, and I'm going to get into that. All right, great. So glad to see you out there. So let's try these equilibrium problems. There's a variety of them here, so let's see how they go. I have a PDF here that will update on the Classroom that is going to update with the answers that I write in. You have a copy that you can print out on a two-sided piece of paper if you like, or it's just a compressed version of this with all the questions sort of with less space. So for the reaction of 2A, there should be a little arrow in here. A converting to B plus C, the initial amount of A is 4.0 molar, and at equilibrium its concentration is 2. What is the equilibrium constant at this temperature? So they're saying that for 2A, there is a conversion to B plus C. And the question is, if you are initially, the initial concentration of A, initial, is 4 molar, give or take, 0.0 molar, then at equilibrium, so this is the concentration of A at EQ, and that is 2.0 molar, what is KEQ? So that's a fun little question. Here, I do like to do an ice chart either way. So ICE. Does anybody have any comments about equilibrium questions? In general, they are thought to be somewhat the hardest concept that we do in this course. So if you are having difficulties, it'd be a great time to drop into any of the chats. I'm checking all my chats here for any problems that we're having. If anybody would like me to try the live chat again, I can try to send out another live call if you think that you would join up. Or you can call me if you want. All right, so we initially have 4.0 molar. And then over here, we have, please let me know if the sound is okay. It looks like I'm overpowering my sound here. Okay, I'm going to quiet down a little bit. And we're saying that we initially have only A, so we don't have any of B or C. At equilibrium, we have 2.0 molar. And that's all the information they gave us. There's one other thing that we do know, which is that KEQ has to be equal to the product of the products divided by the concentration of the reactants squared, or to the raised to its coefficient. So that might be useful later. Now, any changes must be in accordance to the original coefficients, or the stoichiometry. So here we would be looking at some change that's going this way, right? We're changing in this direction. And so that means that we lost some X, we lost some A, and we gained some B and C. And it looks like we gained a little bit of B and C in both cases. Now, in some other questions, we do have to work a little hard to find what the X is, but we can rewrite this as sort of a linear equation. 4.0 molar minus the 2X is equal to 2.0 molar. So what does that mean X is? Well, it looks like X is going to be I think it's 1. Anybody else agree with me? If you want to do some math, you can, of course, you can subtract anything off of both sides. So we can move this over here. So that gives us negative 2x equals negative 2.0. That means dividing by negative 2, divided by negative 2, and you're going to get x equals 1.0. So 1.0. So that replaces this value here. This is now 1.0. This is 1.0, and this is 1.0. So in this case, we now know that the equilibrium concentrations must be 1.0 molar and 1.0 molar. So that's always nice. Worked out well. So we can take all three of these values and we can import those into our calculation over here so that we do KEQ is equal to 1.0 times 1.0 divided by 2.0 to the power of 2. Punch that into a calculator and let's see what we got. We got 1 times 1 divided by 4. That's 1 over 4 really. So we're just talking about 0.25 as our final answer. And so that is what we called a KEQ calculation question. You're given the concentrations, and you need to determine KEQ. Does anybody have any thoughts on that? If you want to shout out in the live chat, I love to know who's out there. So if you want to send me a message there, or if you want to send me a message through Google Hangouts, all of that is good. Looks like we'll be moving over to Google Meet. So if you didn't have enough apps, you can expect to move over to Google Meet soon. Okay, great. So that's that question. That's the first question. Let's check out this next one. This next one has some other parts to it. So the dissociation of acetic acid has an equilibrium constant at blah. The reaction is blah. If the equilibrium concentration of the acetic acid is of moles of this, of water, and that the in moles of water, and that the CH3COO minus is this many moles. We'll calculate the concentration of H plus, which is this one, for this reaction. Okay, so this is an interesting question. We are given an equilibrium constant, and we are given, in fact, two equilibrium values. So let's write out what we have. We have KEQ, which is equal to 1.8 times 10 to the negative 5. I believe that's a real number. And we have the concentration of CH3COOH. Notice that this is at equilibrium. So that's important. And it is 0.46 in 0.500 liters. So that means that it's actually 0.92 molar. And we have the concentration of CH3COO minus at equilibrium. And that is given as 8.1 times 10 to the negative 3 moles in the same volume liters. I don't like having two equal signs in a row. So that means that we actually have dividing by 0.5 is like multiplying by 2. So we have 16.2 times 10 to the negative 3. I'm going to clean that up a little bit. We got to move a decimal place, and we have to lose a value here. So okay, so now in this case we have two equilibrium concentrations. The only equation we need, we don't even really need an ice chart here, is we only need the KEQ expression, or the equilibrium law expression. CH3COO minus times H plus divided by CH3COOH, which I always read as choo-choo. And so we have all of these values. We have this one, we have this one, and we have this one. So all we're missing is the H plus. So we can now insert all of these things into the equation. 1.8 times 10 to the negative 5 is equal to concentration of the ion divided by 0.92, and that is no exponents or anything. And then we complete the question with a little bit of arithmetic and all that sort of stuff. This is a case where having a graphing calculator or something that can solve these types of equations is really helpful. So for example, in this one, I can go, times 10 to the power of negative 5. I can say that's equal to 1.62 times 10 to the power of -2. I'll put an x there for the h. We're going to divide, divide the whole thing by 0.92. I think that should work. And that's the value we get. Would like another significant figure, so I'm a little worried about that. So let's maybe just grab a real calculator and do the work. Won't I be surprised when it turns out 0.8? So I'm going to use they have an e function here. It's a big E, I thought. Huh. Could have sworn there was a big E. Oh, there it is. E -5. I'm going to multiply that by the denominator of the other side, and I'm going to divide that by the numerator of the other side. -2. And wow, it was 0.01. Okay. So however you want to do that math, that's up to you. The result is 0.0010. We only had 2 significant figures to start with, so we're stuck with that. Yep. And so that is the concentration of H+. And that's molarity. There we go. Okay, well, that was fun. I love doing a little bit of math in the morning. Hope you do too. Hey, no comments anywhere, so we're going to keep going. Please, maybe I'll take a quick break for coffee here and see if you have any questions. Okay. Question 3. For the reaction of nitrogen and hydrogen to form ammonia, the initial concentration is 0.32 and the initial hydrogen gas is 0.66. At a certain temperature and pressure, the equilibrium is found to be 0.3. Find KEQ. So it's a similar sort of setup to some of the other questions we've seen here. So we're going to go N2 plus 3H2. Do a little breakdown here. 2 and H3. And I'm going to then think about my initial concentrations, any changes I've observed, and any equilibrium concentrations. So let's see if I have an initial values. I do. I have an initial value of 0.32 for the nitrogen and 0.66 for the hydrogen. At a certain temperature, it's found that the equilibrium value for the hydrogen is 0.30 molar. Okay, so that's very interesting. Hopefully it's as thrilling for you as it is for me. So any changes, assuming that they did not start with any ammonia, any changes must be according to the stoichiometry. Now, one thing to think about is a concept we thought about earlier, which was Q. So remember, we could do a Q test, and Q test is the concentration of NH3 divided by the concentration of N2 and the concentration of H2 raised to the power of 3. And in this case, we would stick in these initial concentrations and see what happens. So Q would be 0 divided by 0.32 divided by 0.66 raised to the power of 2. So that's a concept we did cover earlier. We don't really need to do this in this case because hopefully you'll realize right away that that in this case there's no product in the initial case, so the reaction is definitely going to favor to the right. But I just wanted to bring this thought experiment to its completion. So here we would find that Q is currently 0, and that means that Q is much less than KQ, which is non-zero. At least we do know that KQ is not 0 at least. So if Q is less than KQ, then the reaction is going to shift to the right. So we expect change to right. And so that means that we would expect an increase in ammonia, and we'd expect decreases in our reactants, nitrogen and hydrogen. So that's a way we could use Q in this case. All right, now we've done all the fun stuff, or we've played around. Let's just think about this equation. 0.66 minus 3x is equal to 0.30. So, and this is by this equation, I mean, I'm talking about this little equation that we have sort of formed vertically. Okay, well, there's some manipulation you can do. We see something happening here. Okay, I think I'm going to have to do a little bit of rearrangement, see how it's going. Negative 3x is equal to negative 36, 0.36. And so that means that x is equal to 0.12, right? Okay, that's very good. All right, so then we're going to replace that value, 1, 2, replace this value with 0.12, and replace this value with 0.12. So that means that we are going to get a decrease in 0.32. That is going to decrease to 0.20 molar at equilibrium. And the amount of ammonia is going to go from 0 to 0.24 molar at equilibrium. Okay, so let's plug that all in into an equation. So now we're after KQ, right? So KQ is our end goal here, and that's going to be the NH3 raised to the power of 2 divided by the concentration of N2 and the concentration of H2 raised to the power of 3. So this is actually known as the Haber process. It's a very famous equation and a famous chemical reaction. It was one that was being developed in the purpose of producing nitrogen for the formation of explosives during World War II. A German scientist was working on it. It was thought that if he had succeeded, we would have succeeded at that time. Things would have gone a lot worse. He didn't perfect the process until after the war, where he was given leniency by the Allies because he brought his process over to the West, or to the Allied countries, and they turned the process into a way of forming fertilizer. But until that point, he was very much a sympathizer with the Nazi Party, and there is some debate about whether he should have won the Nobel Prize for his efforts when he was clearly motivated to do this research because he thought it would help his country win the war. But the research did end up paving the way for huge industrial farming, which was only possible because of the formation of ammonia, which can be converted into fertilizer. Okay, so 10.7 is the KQ I found as I filled my time while I was chatting there. And I actually only have two significant figures, so I think I'm going to actually have to go down to 11 as my final number. So there we go. And the other thing that's interesting, I'm going to put this little interest in here because we don't really have any Le Chaltier questions in here. But oops, let me type here. The Haber process has a very high activation energy, XO Is it exothermic or is it endothermic? I'm going to be debating about that. Something that makes it complicated. Yeah, okay. So why is this a problem according to the Schulze? So I want you to think about this question. The Haber process has a very high activation energy, but it is exothermic. So what does that mean in terms of chemical reactions here? In terms of pushing your equilibrium to the right, what is the problem here? Okay. So if you need more time to think about it, pause the video. But the problem here is that this means that you would require high EA requires high temperatures to activate the reaction. But exothermic reactions will shift to the right under high temperatures as the excess energy causes conversion of products to reactants. So remember that if we are talking, oh, not right, left. Come on, John. So if this is our exothermic reaction, N2 plus H2 equilibrium NH3, then it's NH3 plus energy. So if you raise the energy by bringing up the temperature, then you're going to cause a flow of reaction backwards. So the more energy we put in to overcome that energy barrier, the more the reaction actually reverses itself. So what can you do? What options do we have here, and according to the Schulze principle, that can force the reaction in the correct direction? So what other option is there to correct for this shift to the left for this gaseous reaction? So give that a thought. Why have I highlight the gaseous part of this reaction? Well, there is one option that some of you might be shouting at me, which is that you could add more nitrogen or add more hydrogen, right? It's a good choice. You could add more hydrogen, add more nitrogen. That would force the reaction to the right. Costly, you got to get more nitrogen. You know, you got to essentially waste nitrogen. You have to put in 110% nitrogen or 150% nitrogen or more, right? If you want a different option, or one way that you can increase the reaction rate with a gas is simply by increasing pressure. We'll increase the reaction rate of the forward reaction more than the reverse, since there are 4 moles of gas on the right and only 2 on the left. So that's your easiest route. Other options include adding more N2 or H2, or removing NH3. And so they actually developed a technique. The Haber process is a little bit more complicated than just the equation. They knew what the equation they wanted to do. So what they needed to do it fast and efficiently is they essentially they created special reaction vessels that squeeze the chemical reactants together. These reaction vessels cause an increase in the forward reaction because they are squeezed inside of those, and then they also developed a way of removing ammonia from the reaction vessel. So they have a filter system, I believe, and so as ammonia is formed, the ammonia is removed automatically. And this allowed for the even faster chemical reaction through Le Chatelier's principle. It's a very amazing application of this. So yeah, so you know what? Let's see if we can find one right away. Let's look up Haber process. Oh, and they also added a catalyst. So I believe this is it here. I'm just going to add another page. So I have some blank space. So let's see if we can give this a look. So here we have methane that's being burned essentially and converted into hydrogen gas. So here's your hydrogen gas. Here is some oxygen, nitrogen. We can pump those directly. Hydrogen gas is a little harder to create. So then we use the oxygen and any remaining methane to convert over to more hydrogen gas and some carbon monoxide. So here's a sort of 2 equilibriums right here, right? 2 different equilibriums. Then they are pumped through a reaction vessel, 500 degrees Celsius, with a compressor, so high temperature compression, and that forms nitrogen, hydrogen, and CO2, which is a little bit more stable and less reactive. Those are pushed through into a scrubber, what's known as a scrubber, and actually this is probably the compressor over here. So we want to keep that pressure high. The scrubber removes the hydrogen and any remaining water and any carbon dioxide. They are compressed again to keep the pressure up. Now you have nitrogen and hydrogen gas only. Those nitrogen and hydrogen gas are preheated. Then they're sent to a reactor where there's a catalyst. And so that catalyst will bring the activation energy down. And they will be under high pressure again because of the compression. And then the mixture is sent over to a cooling section. So this is where this waste is actually used to heat the water boiler or heat boiler, and that gives you steam, which you can send to like heating up your building or whatever, wherever that heat goes. It's sent off somewhere. And then these less hot products and any remaining reactant are sent into a cooler where the ammonia is formed into a liquid state, removed from the vessel. The ammonia cools at a much lower temperature, or a much higher temperature than the hydrogen and nitrogen. So I'd like to put a little comment there. This is a really clever way of separating out 2 chemicals. So ammonia has a higher liquefaction. What is that called? Condensation point than N2 or H2. So when they go in the cooler, the ammonia, the NH3, becomes liquid, and the N2 and H2 stay gas, so they can be reused in the reaction, in the reactor. And so then you also are using this extra N2H2, you're repumping those in back up into the reaction vessel, so you have excess N2H2. So a very clever system of equilibria. Some really clever ways of removing carbon dioxide. Here the carbon dioxide is removed by the water, so carbon dioxide dissolves more in water. CO2 dissolves in H2O, but N2 and H2 don't. So there's another easy way to remove them. So now that you remove the CO2, you can heat it really high up, or heat it up again, and you won't have any side reactions with the carbon dioxide. And then you can have a straight up reaction between the N2 and the H2 and the ammonia. N2 plus H2 goes back NH3. And there's a 3 here and a 2 there. Anyways, okay, so that's a really cool example of applying equilibrium. All right, given the initial partial pressures of these chemicals at 250 degrees Celsius for the following reaction, what must each equilibrium partial pressure be? So this is a question we've never seen really before. You might be very surprised to see them using atmospheres instead of molarity, but we have for a long time said that that pressure is equivalent to concentration of a gas. So, therefore, atmospheres is an equivalent unit for concentration calculations. And also, therefore, we can use same expressions with atmosphere or with pressure instead of concentration. So our new equation now looks like this: Kp, which is for our Kq with pressure, and we're just going to put the pressure of the reactants, the pressure of PCl3 plus the pressure of Cl2. Oops, not plus, multiplied, of course. I'm going to do a dot for multiplication, divided by the concentration of PC, or the concentration by form of pressure, PCl5. And the good news is there's no exponents, but if there were exponents, we can simply put the exponents on just like normal. Okay, we are given only initial values and then asked to find what the equilibrium pressure is. So this is going to be a full-on calculation. So let's strap in and get ready. We need a really nice equation to work with because we're going to be doing a lot of work here. We're going to need, so I'm building my nicest chart I can possibly find here. Ice, I, C, E. I like to leave myself a little bit extra room in that C slot just in case I need it. I'm going to put a little bit of a break here just so I have a line to follow. Okay, so my initial concentrations are, we do not have to do any multiplication or anything like that. We just are going to drop them in. So PCl5 is 0.0500, and these are atmospheres. 0.150, and that's also atmospheres. And 0.250 atmosphere. And we have a K of 2.135. And we have Kp equals 2.15. So I have a lot of things going on here. One problem is I don't know which way the calculation is going to go. I don't know if I should be shifting left or shifting right. Should I be adding x here or subtracting x? That's a big difference. So we need to do a little bit of work first. We need a Q. So let's do a Q test. We're going to put our products over our reactants and see what the value is. Okay, so 0.75. All right, so that means that Q is less than K, right? This is less than 2.15. So if Q is less than K, that means that the numerator is smaller than it should be, right? Yeah. So that numerator needs to actually be larger than what we have. So to make the numerator larger, I'm going to have to increase the amount of PCl3 and Cl2. I'm going to have to increase the amount of product. This is going to be a really tricky question. What must each equilibrium pressure be? That's initial pressures. Okay. Well, this is going to be a real tricky question. All right. So I want to shift right. And you might not have thought that at first, right? Because if you look at the way the equation lays out, I'm just double checking my math here. Yeah, that's where it's at. Okay, I need to go higher. So I'm going to need some increases here, and I'm going to need to lose a little bit of my PCl5. I am surprised. This looks like an incredibly challenging question. I'm a little worried about how hard this question is. Okay, so 0.0500 minus x, 0.150 plus x, 0.250 plus x. I'm looking for a secret here. See if there's anything that will give away what I want to do. Nope. X and x is multiplied. Yeah, no, it's not. Okay. I actually think I'm going to get stuck in a second. I don't have much of an option here. If I take things too far, the equation I'm going to get stuck with is going to look like this. It's going to be a real mess. 0.150 plus x times 0.250 plus x divided by 0.0500 minus x. So that's the equation we get. Now, this value we do know, it's 2.15. So this is where I'm looking at this equation, I think this is too hard. This is actually probably too hard to actually complete. You would probably want to do this by some calculus or some multi-linear algebra would probably work really well here. I'm going to see, let's see what Desmos says. Desmos is probably not going to like this very much either. So let's just bring that in here. We'll give it a real quick shot, and then I'm gonna give up here. What time is it? Oh boy. Okay. 0.150 minus x. 0.250 minus, plus x. I'm sorry. Plus x. Okay. Oh. Okay. And then I'm going to do the whole thing divided by 0.050 minus x. So, we did. Okay, we got an approximate value here. We got to get real in here. Okay, so about 0.027. So you can see that value there. Should work as x. So let's just see what that looks like. Let's go, you can go 0.150 plus 0.27. And it looks like 272 multiplied by 0.250 plus 0.272 divided by 0.0500 minus 0.0272, and that gives me 0.0272. Should be, this should have given us 1 point. Oh, I got an extra 0. And I bet I put an extra, yeah. There we go. 2.15, so that's pretty good. So we would be pretty happy with that. So this is where I would definitely use some software. It's way too challenging to solve by itself. Sometimes if the values were a little bit more similar, or if there's something else we could do. But we could probably, you know, with a very simple change, we could make this a more solvable problem. But here we're going to get x equals 0.0272. So all I did here was I inserted the entire equation into Desmos up in the top right here. Desmos is a free graphing software. If it's a completed equation, you'll get a line. It sometimes doesn't like letting, the line is not well defined. You just gotta kind of have to zoom in until you get an approximate value by looking at the at where it lies. So I noticed that it's between 0.027161 and 0.27162. Well, I only need 3 significant figures anyways, so that's 0.2716 or 272. You know, we probably would even get a better answer. And then I just double checked by inserting this value of x up into this equation and making sure that it equaled the 2.15. So that's what I did. Hopefully that makes sense to one of you. As I said, this is a very challenging question because of the number of unknowns that we're left with. To do this on paper, there are some techniques we can do, but I'm hoping to release a video later that outlines some of those more advanced techniques. But this is honestly probably the best technique, is just to use a calculator, like a computerized calculator, and to get comfortable with doing that, because that's certainly how I would have done it if I was doing it in the field, for example. As in, like, if I was doing this as part of research, I would never sit around hand calculating anything. I'm always going to use a calculating app of some sort. Okay, so there's our final concentrations and of that question. Now, I believe we are out of time, so I am going to leave it there. Tomorrow, I'm hoping to start solubility. And we actually, I have I have a lab that you'll be able to do at home possibly. So, or at least I'll be able to do at home, is hopefully, and we can try that together. So that will happen later in the week, probably Friday. Yeah, so that's where we're at today. So I'll leave it here. That was a very challenging question at the end, but we did a little bit of learning. Maybe we'll do one more day of equilibrium before moving to KSP. Remember, if you need anything from me, please don't hesitate to email me or to contact me through the Hangout. I am going to create a Google Meet, so you can switch over to the Google Meet app if you like, and that will be an even easier way to talk to me. Have a great day, and we'll talk to you soon.